other thing. So welcome to the electronics course. This is now module 15, and we're going to be talking about inductors. So this is a continuation on from resistors, which we did a while back. And we're going to talk a little bit about inductors, inductance, uses of them, series parallel circuits, what happens in DC, what happens in AC, and then we'll talk a little bit about the inductive reactance. And then next week we'll talk about capacitors, which is opposite of the inductors. And inductors are more like resistors. And you can think of inductors basically as a coil of wire. So it's another electrical component. So far, we've only looked at one component, which was the resistor. As I've said, the inductor is similar to a resistor, but it's a coil of wire instead. And it's used to store magnetic fields. And here, this is a symbol of an inductor, which is basically looks like a coil of wire. And then you have different types of inductors here, either on this round round one is called a toroid, and it stores the magnetic field, and the unit of measure is the Henry. So some of the uses of this, and we'll cover some of these in more detail in other events, is a transformer, a relay, electromagnet, a generator, an alternator, and a motor. Here are different types of inductors. And you measure inductors in Henry. So one of the parameters, the main parameter, is the number of turns. So the more turns you have, the more inductance. And this relates to the length of wire, also to the length of the coil. So if the coil is spread out, you get less inductance. If it's closer together, you get more inductance. And then also, if you spread it on a bigger coil, if the size of the turns are bigger, you get more inductance, and less inductance if it's smaller coils, smaller turns. But the most important ones is basically the number of turns and also your core material. So if you have an air core, you get less inductance than if you have a ferrite or an iron core right here. And they measure permeability, and like the permeability of air is 1, and then some of these cores are up to 600, and then depending on whether it's an iron core or a ferrite core will determine the frequency response of it. One of the things you have to be careful of when you have these is, if you put a lot of currents through them, they'll heat up. And if the ferrite material gets hot, it loses some of its characteristics and doesn't work as well. So if you put inductors in series, it's like a resistor. So you just add up. So to find out your inductance, you just add L1 to L2 together, and that's you get your value. And inductors in parallel is the same like a resistor. You can draw it this way or you can draw it this way. So it's basically 1 over L1, 1 over L2, 1 over Ln. You take the reciprocal of all of these, add up the reciprocal, and then take the reciprocal of that. And that gives you that value. So it's the same as you would do for a resistor. Some of the tricks that you have is if you have only 2 inductors, you can multiply them and divide it by the sum of them. and that'll work. And then also if you have like 10 inductors with all of the same value, you just divide that value by 10. If you have 5 of them, all of the same value, you divide by 5 in parallel. So same as resistors. So uh, so what happens here is that when you apply electricity to it, it builds up a magnetic field. And then when you take the electricity away, the magnetic field drops. So if you build a little circuit like this and have a switch, and you have an inductor and then a load and then a battery. So if you look at your supply current, when the switch is in A, nothing is connected. And then when you switch it to B, you're going to start loading up the inductor. So the value of the current will increase until it reaches the maximum. And then when you flip the switch over to C, you've disconnected the battery, but you have now this resistor in here, which is the load. So now you're discharging the inductor. So then this falls back down again. And so what you have here is a time constant. And so you have your time constant here, and you have some formulas here. These are exponential formulas like E to the minus time constant. This is your natural log um, function here. But you don't have to worry about calculating these. The thing here is to remember, at 0 time constant, after 1 time constant, it's 63% of the value. At 2 time constants, it goes up to 86. 3 time constants, 95. 4 time constants, it goes up to 98. And 5 time constants goes up to 100%. So it'll be a curve up here. And then for decay, it's just the opposite. It'll start going down. And so the current will go up here, and then the voltage will go down, and then it'll just be the opposite for the voltage. Um, so when so on in the advanced course, you actually have to do some of these calculations, but for capacitors, not for inductors. But it's pretty well the same curve, but different values. So for the advanced course, you'll need to know this here, and they'll ask you, how much is the capacitor charge in 3 time constants and things like that. So it's the same for the inductor. The time constant here is the inductance divided by the resistance, so L divided by R. And we'll look at capacitors next week. So when current goes through a wire or an inductor, it creates a magnetic field, and these are magnetic field lines, and they tend to go from north to south. And it creates a magnetic field. When you eliminate the current, these magnetic fields collapse, introduces some back EMF into the coil, and if you're not careful, these can damage some of your solid state equipment. There is a statement called Eli the Iceman. And so today we'll talk about Eli, and next week we'll talk about ice. So Eli means that the voltage E leads the current. So when you look at a resistor, both the voltage and the current are traveling together, and there's no difference between the two, and this produces heat. But in an inductor, what happens is the voltage goes through first. The current needs to create a magnetic field, and it takes some time to create this magnetic field because of those curves we saw back here. So it's delayed. So you got Eli, so voltage leads current. Or you can look at it as current lags the voltage. Just remember, most common is voltage leads current. L stands for lead. So when you actually look at this, and we may actually look at this on an oscilloscope, I haven't found something that I can actually do all of this yet, but I'm working on it. So as you can see, and this is a little bit confusing because we said the voltage leads the current. So the voltage starts off here, and then the current starts later on. So when you look at this, it actually looks backwards, but the current, the voltage leads by 90 degrees, although the thing is deceptive when you look at it. And in the capacitor, just the opposite is different. So the difference between these two sine waves is known as phase. And in this circuit, because we just have an inductor, it's 90 degrees out of phase. If we were 180 degrees out of phase, this curve would cancel this curve and we would get a straight line. So what happens is that with inductance, there's a relationship between reactance and frequency. And in this case, it's a relationship. So as the frequency goes up, so does the reactance. And the reactance is measured in ohms or calculated in ohms. And to calculate the reactance, you take 2 pi, which is 3.14 times 2, so 6.28 times the frequency in hertz times the inductance in henries, and you get a value called inductive reactance. And the thing here to remember is that as the frequency goes up, so does the reactance. Next week, you'll learn that for capacitors, it's just the opposite. So instead of going up this way, for capacitors, it's the opposite way. So when you look at this, because the ohms are going up, so your inductive reactions goes this way, and as it goes higher with Ohm's law, the current actually goes down as the frequency goes up. And so one way you can think of this is that an inductor blocks AC. So you have DC and AC going to an inductor. The DC will go through, the AC gets blocked, and it's just the opposite of a capacitor. So DC passes through and AC gets blocked. And this is why inductors are often used in DC power supplies to remove the AC ripple, because the DC will pass through and the AC gets blocked. So any questions about inductors? We'll look at capacitors, and then we'll get into some practical things. And then we'll also look at some things about, when we get to power supplies, filters, and things like that. So let me
I have a question.
Okay.
I forgot. I used to know this stuff a long time ago. The left-hand rule and the right-hand rule.
Yes.
The right-hand rule, I think, was used for current and inductance, magnetic induction, left-hand rule, or did I get it backwards?
No, you got it right.
You've got it right.
Okay.
Yeah, one rule tells you which way the magnetic field flows based on current, and the other hand tells you which way the magnetic field flow based on electron flow.
Okay, then the next question is, with the time constant,
Yes.
is there a difference if you use AC or DC? Because if I remember, DC has 0 time constant. Well, AC takes time. to build up inductance,
Well, I think
depending on the frequency.
yes, but I mean, here we're just looking at DC.
Yes,
So
okay.
DC follows this curve here. So it takes time to build up the magnetic field. So you have a time constant. And when you look at AC, then you end up getting you're getting more this curve here. So when you're down here at DC, you're building up your time constant. So it happens faster as you go up in frequency.
Oh, okay, yeah, so it does make a difference depending on frequency.
And yeah, and we'll get into things like resonance and filters and things like that in future discussions. Any more questions? Okay, let me stop the sharing and stop the recording.